I'm going to begin this video by writing down a chemical formula, C6H12O6. Some of you who study biology, you may recognize this molecule. It's called glucose. So this is the glucose molecule. It's critically important for human beings because it's what provides our main energy source. So this is the main energy source, the main sugar that we get from eating carbohydrates. When we digest them into this stuff. And this is essentially the fuel for our bodies. So that's glucose. That's not really what's important here, though. What's important here is that we recap something we've learned before. We learned what this chemical formula means. So what do the little 6 mean? The little 6 means that there are 6 carbon atoms. That's what that means, carbon atoms. The 12 means that there are 12 hydrogen atoms. And the 6 means that there are 6 oxygen atoms. So this type of chemical equation here tells us an actual number of atoms that are in this molecule. Okay, so this here is a molecule. All these atoms are connected together, and this formula here tells us exactly how many of each type of atom there are in a formula. Because of that, this here is what's known as what we call a molecular formula. And we're very lucky that we live in an age that in chemistry, nowadays, we have techniques and methods that can allow us to work out what the molecular formula is for every substance. So we know for every different chemical, we know exactly how many of each type of atom are in there. So this here is what we call the molecular formula, quite detailed. It tells us what's in it and how much of each, how many atoms of each one is in it. But chemistry wasn't always like this. We didn't always know this level of detail. Okay, so if we think back, though, we'll try and figure out how did scientists first start to come up with chemical formulas. Well, if we say, okay, let's say back in the day, someone was doing an experiment and they had a little container, and inside the container, they had some glucose. So they put that stuff that we just had, let's say it's a white powder. Now I don't want to color it in white or you won't see it. So they've got a white powder, and underneath that white powder, they heat it up. Okay, so what is the red stuff? The red stuff is glucose. Let's say they had 10 grams of glucose. What's going to happen during this experiment, what would they observe, is that glucose is essentially what's going to be left behind. The glucose is going to burn, and what's going to be left behind is the black carbon. So the carbon from the glucose that we know is in there is going to be left behind, and the two other things, oxygen and carbon, would be released as gases. Oxygen, sorry, not carbon, oxygen and hydrogen would be released as gases. And scientists, basically, what they would do is they would work out, well, how much carbon is left. So we started with 10 grams, how much carbon is left, and then would collect the oxygen and hydrogen as it was being given off. They collect these two gases, measure them, and by basically measuring the different quantities that they produced here in this reaction, they would essentially be essentially able to work out that this substance, glucose, was made of 1 part carbon to 2 parts hydrogen, so twice as much hydrogen, 2 parts hydrogen to 1 part oxygen. So not as much detail as before. I don't know the exact amount of atoms. They just know that looking at the masses and the volumes, it must be the amount of carbon and oxygen is around the same, and then you have twice that amount of hydrogen. So they would have probably written it like as a ratio like this. So 1 part carbon, 2 parts hydrogen, 1 part oxygen. Now notice that this is not the same level of detail as what we currently know with the exact amount of atoms. This would give us something like this formula, CH2O. That's kind of our ratio expressed in a formula, CH2O. Now, what type of formula is this then? Because this definitely isn't a molecular formula. It doesn't tell us exactly how many atoms are there. It's just a ratio, or the lowest possible ratio of these different elements that are in the compound. 1 part hydrogen, 2 parts hydrogen, sorry, 1 part carbon, 2 parts hydrogen, 1 part oxygen. Now, evidence that's collected like this using experiments is what we call empirical evidence. So empirical evidence is direct evidence that's collected by experiment. It's not something you read in a book. It's something that you actually go and measure. This is what we call empirical evidence or empirical data. Empirical evidence. So this is empirical evidence because it was collected by actual people doing actual experiments. It wasn't a simulation on a, it wasn't a computer. It was actual people collecting direct evidence. And because of that, this thing here that we have has become known as the empirical formula. This is all chemists would have had for years and years. They would have had the empirical formula of everything. They would have known, okay, what's in it and what ratio they're in, but they might not have known exactly how many atoms of each was in that substance. How does that link to the modern day molecular formula that we know? Well, let's say, for example, glucose is C6H12O6. We know this now. Well, what's the ratio in the molecular formula here? Well, it's 6 is to 12 is to 6. 6 carbons, 12 hydrogens, 6 oxygens. Now, if you look for the lowest common multiple here, lowest common multiple, make this as simple, so basically simplify this line. What you'll see is, okay, well, you can divide all these numbers by 2 to make this 1 is to 2 is to 1. And now all of a sudden you can see that empirical formula, CH2O. So the empirical formula links to the molecular formula by essentially multiplying the whole thing by some factor. In this case, you'd have to multiply everything by 6, but don't worry too much about that for now. I just want you to know the difference between the molecular formula and empirical formula. Empirical formula is always the simplest ratio where everything is a whole number. It doesn't necessarily give us information about the exact numbers of atoms, like this one does. So the top one, the molecular formula, is more useful nowadays, but we have to appreciate and be able to figure out where this information came from. It came from empirical formulas from people doing experiments in the past. So at this stage, what I'm going to do is we're going to just show you the 2 actual definitions that we need to learn here. So we've got empirical formula, and hopefully you understand where that comes from now after my explanation, and molecular formula. Now you see that they're in red here, so I suggest that you make a note of them in where we usually do in our definitions dictionary. And if you think you might need to have a read over that again, some of it's gone over your head, you can have a quick read of these little sections in between. And if you still don't understand, I suggest you go back and watch parts of the video again. So go ahead, write them down. We're not done yet, by the way, so just pause the video, write down your definitions. Okay, so hopefully you've had a look at those. I just want to show you something now. I'm going to show you 4 different substances. So here we've got C2H4. We've got C3H6. We've got C4, sorry, I'm making lots of mistakes today. C4H8. And we've got C5H10. 4 different molecular formulas. They're all very similar in that they only have hydrogen and carbon, but you can clearly see that they have different numbers of hydrogens and carbons, which makes them different substances or different compounds. These are different compounds for sure. Different compounds. With 4 different molecular formulas. So different molecular formulas. Molecular formulas. But I want you to notice something. Each of these has the exact same empirical formula. So in this case, the lowest common multiple of these 2 numbers would be 1 part carbon, so C1, 2 parts hydrogen, CH2. So the lowest common multiple of these is 1 to 2, or the lowest common ratio, I suppose, the simplest ratio, 1 is to 2. So 1 carbon to 2 hydrogens. It's the same here. The ratio here is 3 to 6. We can simplify that. 1 to 2 again would be the simplest ratio. So CH2 is also the empirical formula. Here the ratio is 4 to 8, 4 parts to 8 parts, and we can simplify that, divide both by 4, and you're going to get CH2 again. And this one we're going to see is also CH2. So 4 different formulas, so 4 different molecular formulas, but they all have the same empirical formula. We can find this quite a lot in families of chemicals. And what you will find is that if you look at all of these things here, they will all be very similar in their properties. Similar properties. So if one of them is a gas at room temperature, they're probably all gases at room temperature. If one of them is non-polar, they're probably all non-polar, because they all are just a multiple of this same empirical formula. Okay, you can probably predict what the next one in this family would be. These all belong to a family. If you can go ahead and think about now what the next one in this family would be, you go ahead and think about that now. Yeah, so hopefully you've been thinking along the lines of C6H12. Yeah, and exactly that will be the next one in this family with the same empirical formula. So you see how that works. All right, so a couple of questions to practice now. We're looking at question 20, and this one should be nice and easy to get you started, and then you have to do the same for each of these. Now be careful, they might already be in their simplest form. They might already be you mightn't be able to, the empirical formula might be the same as the actual molecular form if you can't simplify it. Remember, the numbers must be whole numbers. You can't have 1.5 of an atom or 0.5 of an atom. That's important. Okay, so they have to be whole numbers. All right, so pause the video, go ahead, do them, and we'll see you in the next lesson.